in today's class, we'll be looking at heat transfer under thermodynamics. We'll be looking at what? Heat transfer. We'll be looking at heat transfer under thermodynamics, right? Now, when we say heat transfer, we want to understand the concept behind heat transfer, meaning what does heat transfer mean, right? Bringing it back to what we know, when we started thermodynamics as a course, right, we've discussed all the terminologies to be used, which are the what? Open system and closed system, right? We said we have what? System. We have system. The two types of system here are what? Open system and what? Closed system and closed system, right? Now let's define what open system and closed system is. You know what distinguishes between open system and closed system? They are the energy in form of heat and work, or the quantity of matter. Meaning you want to define what open system is and you want to define what closed system is. You can define these two systems using what? Energy. When we say energy, meaning energy in form of heat and work, and what? Quantity of matter. So we are saying that what distinguishes between these two systems are energy. When we say energy, meaning in form of heat and what? Work. Also quantity. Now we said under open system and closed system, what distinguishes between open system and closed system is what? Energy in form of heat and work, and what? Quantity of matter, right? So why are we doing all this? We are doing all this because we want to understand what it means. With the understanding of what it means, we can relate it to what? Heat transfer. With the understanding of what it means, we then relate it to what? Heat transfer, right? Now, by definition, what is heat? By definition, let's define what it means. Heat is a transient form of energy. Heat is a transient form of energy that can be found between the boundary of the system and its surrounding. Heat is a transient form of energy that can be found between the boundary of the system and its surroundings, right? Then let's bring it back to open system and closed system. If truly that definition is correct. You know, when we say open and closed system, let's say you have a system, right? Consider this as a system. Let's consider this as a system. This is our system, right? This is our surroundings, right? Why the difference between your system and your surrounding is called what? It is called the boundary. It is called the boundary. So we are defining it as a transient form of energy that can be found between the boundary of the system and the surrounding, right? Now, let's define what open system and closed system is. The main topic is what? Heat transfer, right? We want to understand the word heat. By the time we understand what it means, then we relate it to what? Heat transfer. We now said we discussed what we call system when we started thermodynamics as a course, right? Under system, we have open system and we have what? Closed system, right? What distinguishes between open system and closed system? The first one is energy. When we say energy, meaning energy in form of heat and work, right? While the other one is what? Quantity of matter. But we are doing all this to understand what it means, right? With the understanding, you relate it to heat transfer. We now said diagrammatically, say this is your system, this is your surrounding, while this is your what? Boundary, right? So let's define what open system is. Or before then, what is heat? By definition, heat is a transient form of energy that can be found between the boundary of the system and its surrounding, right? So we want to know if this definition is correct or not. If this definition is correct or not. So we are bringing back to the definition of open system and closed system. By open system is a type of system where the energy in form of heat and work and quantity of matter can cross the boundary of the system to the surrounding. Can cross what? The boundary of the system to the surrounding. Meaning that if this is your system, meaning we have energy inside the system and we also have what? Quantity of matter inside the system. If these two can cross the boundary of this system to the surroundings, it becomes what? Open system, right? But if energy in form of heat and work cannot cross the boundary of the system to the surroundings, but quantity of matter can cross, it becomes what? Closed system, right? It becomes closed system. So keyword from that definition is that when we say energy, meaning heat and work, they are found between the boundary of the system and its surroundings. You understand what I'm saying? When we say energy, from the definition, we are only interested in what energy in form of heat and work is saying, right? So we are saying that energy can be found between the boundary of the system and its surroundings. So when we define heat as a transient form of energy that can be found between the boundary of the system and its surroundings, meaning the definition is correct, right? The definition is correct. So what it is saying is that it is just telling us that we have energy, meaning how energy is being found between the boundary of the system to the surroundings. But when we say heat transfer, how do we transfer this energy, right? When we say energy, energy means what? Heat and work. Meaning in this aspect, we are referring to what? Heat transfer, meaning heat as a cause, right? While the other one, work. I get me. So in thermodynamics, we said that we are going to treat heat separately, meaning heat as a cause, or it's a subtopic, while work as a subtopic on its own. So meaning that heat is a transient form of energy that can be found between the boundary of the system and its surroundings. Are you getting me? So the essence of all this explanation is that we want to see that heat, or we want to understand that heat is a transient form of energy that can be found between the boundary of the system and its surroundings, right? So if that's the definition for heat, what then is the definition for heat transfer? What then is the definition for heat transfer? Heat transfer is the transmission of energy. Heat transfer is the transmission of energy from one region to another region. From one region to another region by the virtue of temperature difference. By virtue of temperature difference. Or you say by change in temperature. Right? We said by definition, what is heat transfer? Heat transfer is a transmission of energy from one region to another region by virtue of temperature difference. So what we are saying is that you want to transfer it. Before it can be transferred, you are referencing to regions, meaning you have your initial region and you have your final region. So diagrammatically, let's see what that definition is saying. Consider this simple solid block. Say this is your first region. Okay, we want to follow what that definition means. Meaning word for word, we want to follow what the definition means, right? That definition is saying that heat transfer, it is the transmission of energy from one region to another region by the virtue of temperature difference. Meaning before it can be transferred, we are referencing to the first region and the second region by the virtue of what? Temperature difference. Meaning the first region has its what? Temperature. The second region also has its what? Temperature. Right? We now said consider this diagram. If this is your diagram, say this is your first region, consider this as your first region. Consider this as your second region, right? Consider this as your second region. Meaning that this first region, it has its own temperature, say T1. This second region also has its own temperature, T2, right? The difference between this first region and this second region, X meter, right? Then this is the cross-sectional area for this solid block. This is the cross-sectional area, right? Then of course your heat, heat transfer. Heat transfer is the transmission of energy from one region to another region. So this is the first region, this is the second region. The difference between this region, you have a distance, say X meter, right? Moving on, what do I have again? The difference between the first region and the second region by the virtue of what? Temperature difference. Meaning for this first region, you have your temperature, your initial temperature, which is T1. This second region, you have your final temperature, which is what? T2, right? Meaning you want to transform energy from this first region to this second region. The question now is, what energy are you transforming? What is the nature of the energy you are transforming? Is it energy in form of heat or energy in form of work? Energy in form of heat. We said heat transfer. When we say energy, energy means is either energy in form of heat or energy in form of what? Work. So meaning from this first region to this second region, you are transferring what? Heat. You are transferring heat, which is letter Q. Take note that this heat transferred is at right angle to the axis of this block. It is at what? Right angle to the axis of this block. Meaning it is at right angle to the surface area of this solid block. So by definition, we said heat transfer, it is the transmission of energy. What's the energy? Heat. Transmission of energy, meaning transmission of heat from one region to another region by the virtue of what? Temperature difference. Meaning before heat can be transferred from this region, which is the initial region, to this second region, which is the final region, there must be a change in temperature. There must be what? Change in temperature, right? Now, meaning, take note that your initial temperature, okay, we said there must be a what? Change in temperature. Mathematically, when we say change in temperature, mathematically, what does it mean? Is it T1 minus T2 or T2 minus T1? T2 minus T1. But for this very guy, which is heat transfer through a single solid homogeneous block, your T1 must be greater than T2. Your T1 must be greater than T2, meaning that change in temperature is equals to T1 minus T2. That is, T1 must be greater than T2. So what we are saying is that before this heat can be transferred from this first region to this other region, this T1, which is the initial temperature, must be greater than this final temperature. So take note of that. T1 must be greater than what? T2, right? Meaning T1 must be greater than T2 before what? Heat can be transferred. So that's what the definition of heat transfer means. So we are saying that heat is a transient form of energy found between the boundary of the system and its surroundings. But heat transfer is the transmission of energy from one region to another region by the virtue of temperature difference. So heat transfer deals with how it is being transferred, with its mechanism, meaning how do we transfer this heat? What are the mode of transferring heat? Unlike heat, we saw that heat is found between the boundary of the system to the surrounding. It is transferred from the boundary of the system to the surroundings. But heat transfer, it is telling us that how do we transfer this heat? We already have the understanding that it can be transferred, right? It can be transferred from a particular region to the other region. But the question is, how do we transfer this heat? How do we transfer this heat? So this brings about the mode of transferring heat, meaning the mode of transferring heat. So we are saying mode of heat transfer. Mode of heat transfer. The first mode of heat transfer is called conduction. Number 2 is called the convection. While the last one is called what? Radiation. The first one is what? Conduction, convection, and radiation. How do we transfer it through conduction? How do we transfer it through convection? And lastly, how do we transfer it through radiation? Take note that for each mode of transferring heat, they have their respective way of transferring the heat, right? This first one, it is transferred through a solid body. It is transferred through a solid body. Convection, it is transferred through fluid. Heat is transferred through fluid. When we say fluid, fluid can be a liquid or a gas. You can refer fluid as what? Liquid, gas, right? Or air, right? While the last one, we are saying that conduction, it is transferred through a solid body. Convection, it is transferred through what? It is transferred through fluid. When we say fluid, meaning liquid, gas, or air, right? Then lastly, for radiation, it requires no medium. It requires no what? Medium. When we say it requires no medium, meaning electromagnetic wave. You know, when you say electromagnetic wave, by definition, they require no medium for their propagation. These are the medium of transferring it through each mode. So for this last one, it requires no medium. When we say it requires no medium, meaning electromagnetic wave. So to understand that better, by electromagnetic wave, we are saying that it requires no medium for their propagation. So if radiation, it is no medium. If radiation is no medium, meaning at the same time, it means what? Electromagnetic waves, right? Any question? No question. All right, let's take the first one, which is conduction. Let's take the first one, which is conduction. Now, you know, we said conduction takes place through what? Solid body. The illustration we did here, this is a typical example of a solid body. This is what? A typical example of a solid body. You know, I said diagrammatically, consider this simple solid homogeneous block, right? Consider this simple solid homogeneous block. So we are saying that this is a solid body. So any mathematical formula that will be deriving from this illustration, make use of it in what? Conduction. Are you getting at all? Now we said conduction is what? Solid body. Meaning the mode of transferring it through conduction, it requires what? Solid body. Then when we did our illustration, meaning diagrammatically, we drew this diagram, right? And from this diagram, we said, you recall that I said, consider this simple solid homogeneous block. So what this diagram means is what? A solid body. So any mathematical formula or any mathematical equation you'll be deriving from this illustration, that's what governs what? Conduction. That's what governs conduction, right? Looking at this solid body, you know, the main aim is what? The main aim is transferring it from this solid body. You want to transfer it from this first region to this second region, right? You observe that we have several parameters hindering this heat to be transferred or affecting this heat to be transferred. Are you getting at all? We want to transfer it from this first region to this second region, right? We want to transfer this heat, which is key. You observe that we have several parameters hindering this heat to be transferred to the other region. The first one is what? Area. The second one is what? Distance. The third one is what? This temperature. While the fourth one is the heat itself. So we are saying that we have several relationships between heat and these parameters. So the first one is that first thing first, let's note the parameters. I'm having Q, which is the heat to be transferred. The next one is area. The temperature, meaning change in temperature, T1 minus T2, right? And the last one is what? The distance. So meaning that before this heat can be transferred from this region to this other region, these factors are considered, which are the area, the change in temperature, and the distance. So you know, when we define heat transfer, we said before it can be transferred, there must be a value of temperature difference, meaning there must be a change in temperature, where the initial temperature must be greater than the what? Final temperature. The initial temperature must be greater than the what? Final temperature, right? In essence, what it means is that the relationship between the heat to be transferred and area, change in temperature, and what? Distance. So the mathematical formula will be having here, or the mathematical formula will be deriving from here. That's the law that governs conduction. Just know that for each mode of heat transfer, for conduction, it has the law governing it. For convection, it has the law governing it. While for radiation, it also has the law governing it. For this conduction, the law governing conduction, it is called the Fourier law of heat transfer, right? While convection, it is called the Newton law of cooling. While this third one, you are going to relate it to wave. When I say wave, meaning reflection, the incident ray, and the reflective ray. You will see all of this later on, right? So what I'm trying to say is that the mathematical expression will be deriving from this diagram. That's the law governing conduction under heat transfer, and it is called the Fourier's law of heat conduction. So meaning from here, with what we have here, we've seen that there's a relationship between heat, area, change in temperature, and distance. The first one is the relationship between the heat transferred and the area. Saying Q is directly proportional to the area. Say this is equation 1. The next one is the heat transfer directly proportional to the change in temperature, meaning T1 minus T2. Say this is equation 2. While the last one is Q inversely proportional to the distance. Say this is equation 3. Combining equation 1, equation 2, and equation 3, meaning that Q is directly proportional to the area multiplying the change in temperature or divided by what? The distance. Say this is equation 4, right? I'm having a proportionality sign relating that to variation, meaning constant is coming in. The constant in this case is K, meaning that from equation 4, I then have Q equals to K multiplying A, all into bracket T1 minus T2, all divided by X. Call this equation 5. Equation 5 is called the Fourier's law of heat transfer. Equation 5 is called what? The Fourier's law. The Fourier's law of heat. Fourier's law of heat transfer. Equation 5 is called the Fourier's law of heat transfer, meaning that the law governing conduction is Fourier's law. Meaning the law governing conduction is called what? Fourier's law. Where this is the equation. Each law has their respective equation. For Fourier's law, this is the equation. The law governing conduction under heat transfer is called what? Fourier's law of heat transfer, right? Where Q is the heat transferred, Q is the rate of heat transfer. Is either you see it as Q or you see it as Q dot, meaning the rate of heat transfer. You know, when you have M and M dot, what's the difference between M and M dot? This is mass, while this is what? Mass flow rate. When you see dot on a particular parameter, meaning with respect to time, meaning the rate at which it is flowing. So in some textbooks, is either you see it as Q or you see it as Q dot. It's still the same thing. Right? So I'm saying that Q is the rate of what? Heat flow rate. Q is the rate of heat flow rate, where the unit is in joules per seconds or watt, right? It is in joules per seconds or watt. The next one is what? Area. The unit of area is in meter square, right? Change in temperature. What's the unit of temperature? Kelvin or degree Celsius. Then my X, meaning distance, I have it in what? Meter. What's the unit of K? What's the unit of K? How do we get the unit of K? Now let's get the unit of K. Substituting the parameters in terms of units. Right? In this case, this is the unit of Q, meaning the rate of heat transfer. This is the unit. This is the unit of area, meter square. This is the unit of change in temperature, meaning Kelvin or degree Celsius. This is the unit of X, meaning distance. It is a meter. The question now is, what is the unit of K, or what is K? K is called the thermal conductivity. K is called the what? Thermal conductivity. So how do we get the unit of K? How do we get the unit of K? Take note that different material has their thermal conductivity. Meaning, when I say different material, meaning insulating block has its own thermal conductivity, cement has its own thermal conductivity, asbestos has its own thermal conductivity. Any material you can imagine has its own thermal conductivity, right? So what is the formula for this? What is the unit of this thermal conductivity? It will always be given a question, meaning the thermal conductivity of any material, it will always be given in question. So the thermal conductivity of an insulating brick will be given, of a fire brick is going to be given, right? Any material, whatsoever the material might be, any material you can imagine, the thermal conductivity will always be given, right? So let's get the units. How do we get units? Let's substitute the unit of each parameter, then make it the subject of the formula, right? By doing that, what's Q? Q is what? Watt, right? Q is what? Watt. So I'm having watt, equating that to K. What's the unit of area? Meter square. What's the unit of temperature? What's the unit of temperature? Kelvin. All divided by what's the unit of meter of x? Meter, right? Meter cancel here. You are left with what? Meter, right? Therefore, watt is equals to the K, meaning thermal conductivity, multiplying meter Kelvin, right? Call this equation 1. From equation 1, make thermal conductivity the subject of the formula. It becomes W, from W equals to K multiplying meter Kelvin. It implies that thermal conductivity K is equals to watt all divided by meter Kelvin. Therefore, thermal conductivity is equals to watt per meter Kelvin, or watt per meter degree Celsius. So substitute what's needed for thermal conductivity: watt per meter Kelvin, or watt per meter degree Celsius. Moving on, we said when it comes to conduction, the law governing conduction is called what? The Fourier's law. Then mathematically, this is the equation for Fourier's law, meaning equation 5 is called what? Fourier's law of heat transfer, where Q is the rate of heat transfer. This is the unit, joules per second or watt. A is the area, meaning the cross-sectional area for a solid block. Change in T is measured in Kelvin or degrees Celsius, while your K, which is the constant, it is called the thermal conductivity, and the unit is what? Watt per meter Kelvin or watt per meter degree Celsius, right? Now from here, let's state the law itself. What we've done here is the mathematical formula and the unit for each parameters. But let's state what this law is saying. But before then, take note that this particular equation is very, very important. This particular equation is very, very important, right? Meaning as we go advanced, you are going to use it a lot. Meaning in our year 3, we are going to use it a lot. You know, what we know in differential equation, we've done ordinary differential equation, right? We've done ordinary differential equation. Have we done partial differential equation? We've not done that. So by partial differential equation, we have different equations. We have the wave equation, heat equation, Poisson equation, and the likes. So what I'm trying to say is that this equation is a lifesaver, meaning you must know this equation offhand. Anywhere, anytime, you must know this equation, which is the rate of heat transfer is equals to the thermal conductivity multiplying area multiplying what? Change in temperature, all divided by what? X. This is the Fourier law of heat transfer. In differential form, you can write this equation as, the partial derivative of u, the second partial derivative of u with respect to x equals to 1 over c square multiplying the partial derivative of u with respect to x. Therefore, you then have the partial derivative of u with respect to x equals to the partial derivative of u equals to the second partial derivative of u with respect to x multiplying c square, where this c square is called the thermal diffusivity. Right? Meaning that this equation, how do we get this differential equation? It is obtained from this very equation, which is equation 5. There's derivation to that, but we don't need that. I'm just telling us that it is a must for us to know this equation. because this very equation is a lifesaver. It's going to help us a lot in questions, right? So moving on, we said let's state Fourier's law. By definition, what does Fourier's law state? Fourier's law, we are stating the law relating it to each relationship. This first one is that Q is directly proportional to area, right? The second one is that Q is directly proportional to change in temperature, right? While the third one is that Q is inversely proportional to the distance, right? Q is inversely proportional to the distance. So we want to state this law based on this relationship. And we've also seen that this area is at right angle to the direction of heat flow. So let's define what the law states. Fourier's law of heat transfer states that Fourier's law of conduction, Fourier's law of conduction, or you say Fourier's law of heat transfer. It states that the rate of heat flow through a simple solid homogeneous block, the rate of heat flow through a simple solid homogeneous block is directly proportional to the area of the solid at right angle to the direction of flow and to the temperature difference across the solid. Can you see what I said? I said we want to define Fourier's law, meaning the law governing heat transfer under conduction, meaning the law governing conduction under heat transfer based on this equation 1, equation 2, equation 3. So following the definition with this relation, I'm saying that Fourier's law of heat transfer, Fourier's law of heat transfer states that the rate of heat transfer through a simple solid homogeneous block is directly proportional to the area of the solid. It is directly proportional, meaning Q is directly proportional to the area of the solid at right angle to the direction of heat flow and to the temperature difference across the solid, and inversely proportional to the thickness of the solid through which the heat flows. That's what Fourier's law of conduction is saying. Meaning, by the time we record this relationship, meaning this first one saying that Q is directly proportional to area, Q is directly proportional to change in temperature, and Q is inversely proportional to the distance, you'll be able to define what the law states. Just know that this first one, it is directly proportional to the area, to the direction of heat flow, right? And this same Q, which is the rate of flow, is directly proportional to the change in temperature of the solid. And this same Q is inversely proportional to the change in temperature, to the direction of heat flow, right? So that's what Fourier's law of heat conduction is saying. With all the understanding that we have, we've defined what heat means, right? We've defined what heat transfer means. We've seen the law governing conduction under heat transfer, right? Now, the next aspect is the analogy between current flow and heat flow. Analogy between current flow and heat flow. But before then, I forgot to define what conduction is. What is conduction? Conduction, by definition, it is the transfer of energy from one part of the substance to that same substance. Meaning, you want to transfer energy. Say you have a particular substance, say a metal rod. That metal rod, you want to transfer energy to the metal rod. Meaning, you are transferring energy from the substance to that same part of the substance. That's the first definition. Or the transfer of energy in physical contact without appreciable displacement of molecules. So by illustration or practically, let's say you have this metal rod. Say this is A, say this is B, right? Let's say this portion of this metal rod, which is A, has been heated, right? This part of your metal rod has been heated. Then you want to transfer this heat to this other portion, which is B, right? Meaning that this heat can be transferred. When it takes some while, this heat will be transferred, true or false? Let's say you have this metal rod. Say this is A, say this is B. Then point A, or you say portion A, has been heated. Then the portion B, meaning part B, has not been heated. But you agree with me that for some while, this very portion, which is B, is going to be heated, true or false? That's what conduction means. Meaning you want to transfer heat from a substance to that same part of the substance. Say this is a substance. You want to transfer it from a substance, from this substance. Say this is the first substance. You want to transfer it from this substance to the same part of your substance, which is B. That's what it means, right? Or transfer of energy in physical contact without appreciable displacement. Without appreciable displacement of molecules. So what that means is that this is case 1. This is case 1. Case 2. Case 2 is still the same idea. Say you have your first metal rod. Say this is the first metal rod. And say you have the second metal rod. Right? Say this is A. Say this is B. Let's say your first metal rod, which is A, has been heated. Meaning this is these two metal rods. They are in physical contact to each other, right? They are in physical contact to each other. So you want to transfer it from this first metal rod to this second metal rod. You are going to do that easily through what? Physical contact. Through physical contact. So we are saying that conduction, by definition, it is the transfer of energy from a substance to that same part of a substance. To that same part of the substance, or the transfer of energy in physical contact without appreciable displacement of molecules, right? So that's what conduction means. But practically, let's understand what conduction means. When we say conduction, for practical explanation, to understand what it means better, imagine you having a pot of water placed on a gas, right, filled with hot water. Then you take your spoon and dip it inside this hot water. You take your spoon and dip it inside this hot water. Immediately you dip your spoon inside your hot water, the part of the spoon that has entered the hot water experience hotness, right? Meaning it has been transferred from the fluid inside the pot to that part, to that very portion of the spoon, right? For some while, that portion transferred the heat to the tip of your hand. True or false? True. So we are saying that conduction means transferring energy from a substance to that same part of the substance. To that same part of the substance. Right? The practical explanation I gave you guys, that's what we are going to use to understand what convention means. That's what we are going to use to understand what convention means. Right? When we are talking about heat transfer, just know that all the mode of heat transfer works together. But we are actually separating it just to understand it better. Right? From the practical explanation I gave you, you will see that it has been transferred from the fluid inside a pot to the spoon, right? Meaning convention. Why is it convention? We said convention occur through what? Fluid. When we say fluid, meaning liquid, gas, or air, right? Without practical explanation, from the fluid inside a pot to the part of the spoon that experience the hotness immediately, convection has taken place. Meaning the transfer of energy, which is heat, from the fluid to that very portion of the spoon, right? That's convection, right? Now from that very portion to the tip of your hand, that's what? Conduction. That's conduction.